Hi folks, today we're going to talk about activity 315. In 314, you compared the genes of 5 different cancer patients, including Mike Smith, to see which ones were turned on and which ones were turned off compared to a normal healthy cell. And by doing so, we can actually compare which individuals have similar cancers versus other individuals based on which genes are turned on and off. Now, in this case, we're going to take a look at something called a gene expression pattern and take a look at how we can use numbers to determine how similar each patient is to each other, and therefore, if one treatment works on one patient, then it should work on a patient with similar gene expression. This is what the future is going towards, to personalized medical treatments. You will not be able to give one size fits all treatments to every single person. We need to know exactly how each individual will respond appropriately. One way we'll do this is we will use what's called the Pearson correlation coefficient, and we'll get to that in a little bit. But basically, it's going to tell us how closely aligned and how closely correlated, how similar two sets of numbers are. So in order for me to see two sets of numbers, I have to have two sets of numbers. And that's what the majority of the math in this activity is. So part one, we are looking at hypothetical gene expression ratios. These are made up numbers, meaning that these tell us how red or how green those colors were in the microarray. We need numbers to be able to tell us how bright of a red it was or how dull of a red it was compared to another patient, because we need to be able to quantify two sets of color data. So what we did was we took two patients, Mike Smith and patient 1, and we looked at 6 genes. And based on a microarray, we gave them numbers to represent how bright those colors were. Positive numbers in this table demonstrate that that gene is upregulated or would have been red in the microarray, meaning that it's expressed more in tumor cells than in healthy cells. So, for example, gene number 2 in Mike Smith was expressed quite a bit more than it was in his normal healthy cells, whereas gene number 2 in patient 1 wasn't quite as red, therefore isn't expressed as frequently compared to normal cells in the tumor cells. A negative number like this negative 1.58 down here demonstrate that that gene was downregulated, which would be a green dot on the microarray, meaning that this individual had that gene turned off when they got the cancer. Those cancer cells don't express those genes, while their normal cells do. Now, the further away from 1 or negative 1 these values are, that means that they're more upregulated or more downregulated in that person. So this gene number 4 is really upregulated in Mike Smith and only somewhat upregulated in patient 1. This gene number 5 is very upregulated in Mike Smith and quite downregulated in patient 1. So we can see some differences between Mike Smith and patient 1. Even though they both have osteosarcoma, they have different genes activated or deactivated in their tumor cells. Now, a value of 1 means that the gene was not affected by tumor formation. So this one right here wasn't turned on when it became a tumor. It was already on. And a value of 0 means that the gene was not expressed in either tumor cells or healthy cells. When that cell became tumorous, it did not turn on. It already wasn't on though, so we don't care much about it. These values are called gene expression ratios, and they help us determine a comparison between different shades of red or green on a microarray in a quantitative way. We now have numbers and data that we can use to compare to one another to represent those colors. We can't just say one gene is more expressed than the other. Now we have a way of saying that gene 4 in Mike Smith was almost twice as expressed as gene 4 was in patient 1. Based on this, I'd like you to answer some questions to check for understanding regarding these gene expression ratios. We won't spend a lot of time on these numbers because in reality they are arbitrary. They are made up. We made them up based on how shiny or bright a red or green is. But I'd like you to tell me which gene was most upregulated in Mike Smith, which gene was most downregulated in patient 1, and are there any genes that are equally expressed in both healthy cells and tumor cells in either patient? Pause the video here. I'll help you on the other side. So the first question was which gene was most upregulated in Mike Smith? That should be fairly familiar for you. Gene 4 was upregulated the most mathematically because it has the highest gene ratio of 4, whereas the other ones are around 3, 3.58, 3.58, and 3. They're all very upregulated, but 1 was most of all. 1 gene was expressed more often in tumor cells at a higher rate than the other genes were. Which gene was most downregulated in patient 1? Well, that should be simple for us to find. We find the negative number there, and that would be gene number 5. Gene 5 is downregulated while every other gene except for gene 1 and gene 6 are upregulated. So this tells me that this gene was turned off in patient number 1, even though normal cells have it turned on. And are there any genes that are equally expressed in both healthy cells and normal cells in either patient? What this is really asking is, are there any cells that didn't turn on when they became tumorous? Are there any genes that didn't turn on when they became tumorous? Or are there any genes that didn't turn off when they became tumorous? Are there any genes that stayed the same whether they were in a healthy cell versus a tumor cell? And that would be when we have a gene expression value of 1 or 0, meaning that there is no change between a healthy cell or a tumor cell. It's either not expressed in both or not affected and turned on in both. And those genes would be gene number 1 in Mike Smith, as well as patient number 1. Seems like there's a similarity there. And gene number 6 was not affected by tumor formation because this value of 1 shows that it was expressed equally in both tumor cells and healthy cells. It was turned on in both. Big left turn into statistics land here. We're going to get to know what is called the Pearson correlation coefficient, also known as R. This is a very common statistic to find in scientific research and medical research, and it tells us how closely related two sets of numbers are. Meaning that if I were to make lines of best fit based on data that I plug into a graph, this being one set of data like Mike Smith and this being one set of data like patient 1, and I plot the points gene by gene inside this graph here, I could either have them look like they make a very straight line, like this one here at number 1, or maybe they mostly make a straight line, but not quite a best great line, Or maybe they are all over the place, like in number 4 right here. Depending on how close they are to that line of best fit, we say that they have a strong or weak correlation. Now, if this line of best fit goes up and to the right, it is a positive correlation, meaning that the values that are on the X, aka Mike Smith's value, and the values that are on the Y, aka patient one's values, go up in the similar manner. They are related in a way that is expected. Whereas a negative correlation, like this one right here, shows us that as Mike Smith's values go up for each gene, patient number one's values go down. So this would show that there is an opposite effect, as in the correlation shows that these two are so different that they are completely negated to each other. One is red, one is green. The sky is blue, the grass is green. These two things do not show correlation in a way that is opposite to one another. Now, there could be no correlation between the two, where they don't show correlation that the two numbers are related in any manner. That would be random scatterings all over the place. And if I were to look at these values and plug them into a statistic calculator, a formula, we can actually get a Pearson correlation coefficient that is going to be somewhere between -1 and 1. The closer that number is to 1, the more it's going to be a large positive correlation, meaning that it's a very strong correlation between the two sets of data. They're very related, and they are related in a way that those two numbers are very similar and they go in the same direction in terms of positive or negative. In fact, anything greater than 0.5 is typically considered a strong correlation. Meanwhile, the closer we get to -1, like this one right here, shows us a negative correlation. It's a strong correlation when it's all the way down to -1, meaning that these numbers are lined up with the line of best fit very well, but they go in opposite manners. One goes up while the other one goes down. One is upregulated while the other one is downregulated. And again, anything above about a 0.5 in either direction is a strong correlation, something that we can trust that the two sets of data are very related, and therefore those two patients should respond to treatments in the same way. Or if it's a negative correlation, they should respond in opposite ways. If we use treatment 1 on patient 1 and there's a negative correlation, we definitely shouldn't use it on Mike Smith because things will go south very quick. So here is the moment where you get to decide how much of a nerd you are. I have 4 patients compared to Mike Smith right here, and each of them have their own gene expression ratios for each of the 6 genes that are being questioned for cancer. In this first step, I show you an equation for you to be able to calculate your own Pearson correlation coefficient. Certainly try it if you like, but instead I'm going to prepare a spreadsheet for us and allow you to see how Google Sheets and Microsoft Excel can do this for you without you having to lift a finger. Literally, you're going to type in some numbers and be done. So in Canvas, I want you to find a sheet that is called the Pearson Coefficient Practice, and it has our numbers from 315 in it already for us. I know, I'm too good to you guys. We are going to take the time to create Pearson correlation coefficients that compare Mike Smith to each of these patients, therefore telling us how likely each of those patients' drugs are going to work on Mike Smith. Each of them got a different drug, and depending on the genes and their expression, we might be able to determine which of those drugs work really well on Mike Smith. We'll do this by calculating a Pearson coefficient correlation. We'll click this box that we need to have for Mike Smith and patient 1, and I'm going to hit the equal sign. You can follow along with what I'm doing up here in this bar at the top. I'm going to type in Pearson. You don't have to write it in all caps. We're just going to type it in that box there, Pearson, and I'm going to hit an open parentheses. And what this is telling Google Sheets is, hey, I want you to run the formula that we have for the Pearson coefficient so that I don't have to do it on my own. In order to do this, I need to tell it the two sets of data that I wanted to compare. And we'll start with the patient that we want to compare to Mike Smith, because we're comparing each of these patients back to the original guy, Mike Smith, to see how closely aligned they are to him. So I'm going to have them listed as first. So all I did was I clicked in C3, that's the 0.00 for patient 1, drug 1 at gene 1, and I clicked and dragged all the way down through gene 6 to highlight every single one of those numbers. You can see the orange dotted line around those boxes to show me that's the data that I selected. I'm then going to hit a comma, and I'm now going to select Mike Smith's data in the same way, clicking on this 0.0 for gene 1 and dragging down to gene 6 here. I'm going to close the parentheses. I'm going to double check my numbers here and make sure that each of these have the same start and finish point. They both start in cell C or cell 3 and end in cell 8. One is in column B, that's Mike Smith. One is in column C, that's patient 1. Things look good. I'm going to hit that enter button, and it now gives me a Pearson correlation coefficient that I can use to tell you that, boy, Mike Smith and patient 1's genes really don't line up quite as well as we'd like them to. There is not a strong correlation between the two. I would like you to do the same thing for Mike Smith and patient 2, comparing this set of data to this set of data. Mike Smith and patient 3, this set of data to this set of data. And Mike Smith to patient 4, this set of data to this set of data. Pause the video here. I bet it's going to be easier than you think. Let's see how you do. So we did our calculations, and what do we get? Mike Smith and patient 2's coefficient correlation, or correlation coefficient, is 0.959, which is a very, very strong correlation and a very positive one, which means that these guys are pretty closely aligned in their genes, aren't they? Mike Smith, patient 3, strong correlation of 0.755, just not as strong as patient 2. Mike Smith and patient 4, a strong correlation, but it is a negative correlation of negative 0.944. What does that mean? Well, if I give Mike Smith patient 4's drugs, then we might have an adverse reaction in Mike Smith instead of a positive reaction that patient number 4 had, or vice versa. If I gave patient number 4 a particular drug and it had adverse reactions in him, maybe it just might work in Mike Smith. Now, personally, I will always go with positive correlation to determine my treatment plans. So I would give Mike Smith patient number 2 and their drugs that they got, which is a higher correlation anyways. This 0.959 is more correlated than a 0.944, whether it was positive or negative, anyways. So in steps 3 and 4 in part 3 of 315, it is asking you simply to analyze what we just did. And we just analyzed it together, so spoiler alert for you, sorry. To recap what's going on, when we calculated those correlation coefficients, when it's positive, it means that the gene expression profile behave in a similar way. And the more positive that number is, the stronger the relationship, meaning the more likely that treatment is going to work. When the correlation coefficient is negative, it means that the gene expression profiles behave in opposite ways. And the farther away from it is from zero as well, the more strong the relationship is. When the correlation is 1, it is perfect. It means that the gene expression profiles are identical. I highly doubt you're going to find something like that. And when the correlation coefficient is 0, it means that the gene expression profiles behave in an unrelated manner. They are not correlated, and you should not expect to find any statistical meaning behind those numbers. Based on that, which chemotherapy medication should Mike's oncologist prescribe? Well, we can pretty obviously see Mike Smith should get patient two's drugs there. Here's what I would expect on a mastery check. You should be able to look at a table just like this and be able to, using this statistical analysis, tell me which which patient's treatment should work for Mike Smith. You will not have to calculate a Pearson correlation coefficient. I will always give you Excel sheets if I ever want you to actually calculate it. I say let the computers do their job and let me do mine. But you will be given these values and you'll have to tell me exactly what they might mean in terms of whose treatment should work on Mike Smith. Make sure you answer these conclusion questions the best you can. I'm willing to help out with that. Please feel free to ask me any questions about any of the statistics. I hope this made a little bit of sense to you. If it did not, feel free to ask me questions to help you along the way. I'm happy to help. Promise.